All right, this is Big O notation, and these are honeygram O's. It's an incredible cereal. I don't know if you've ever had them. They're like big Cheerios, super crunchy. Yeah, they're bigger than Cheerios. And then the middle of them is filled with goodness. They will destroy the top of your mouth if you're not careful in how you chew. I think they're delicious. They are very sweet. My mom would not allow them, but my grandmother did. As computer scientists, we heart algorithms. Heart means like or love. Yeah, so we really care, like kind of our bread and butter. Bread and butter? Our meat and potatoes is algorithm. This is what we use to solve problems. It's fun to solve problems, and it often can pay the bills. As we are looking at algorithms, we often want to ask, well, which algorithm is better? Is it better to do it this way or this way? And I think this is the fundamental question that is underneath all this big O stuff. Why are we going to create this notation, do this analysis of complexity? It's so we can decide, is this way better or this way? And exactly how much better is it? We really heart speed. That means we really like it, Jordan. We want stuff to be fast because performance is important, especially as we're working in a business environment where time is money. We want to be able to capture performance so that we can improve it. Capture it meaning define it precisely. How do we define performance? There's at least two ways that we're going to measure kind of the cost, the complexity of an algorithm. One is in time, and that's the more common thing that we do. How many steps is it going to take to complete this algorithm, where every step, really, at the end of the day, gets mapped down into some basic operation on a CPU, and that basic operation has to take some amount of time. It might be a nanosecond. It could be smaller than that or bigger than that, but a bigger number of nanoseconds is always bigger than a smaller number of nanoseconds. You can't disagree with that. And a bigger number of milliseconds is bigger than a smaller number of milliseconds. So when we do this analysis, we're going to step away and not worry about actual seconds, but more about steps. But what we're measuring, though, even though we don't say seconds, is time. How much time is it going to take to run this algorithm? Another way of measuring, it's another cost of our algorithm, is its memory. How much memory? On a computer, this would be in RAM, but how much memory, how much storage do we have to invest for this algorithm to run? And different algorithms do make trade-offs between time and memory. This is something we've already seen in this class. What's something that we kind of traded off in terms of a linked list? We traded time and memory complexity. Mm-hmm. But just in terms of a linked list, we said we could do something in two ways. One way would take more time, one way would take more memory. You know what I'm talking about? We could store the tail. Okay, yes, we could store the tail or compute the tail. I wasn't even thinking about that. That's a good example. I heard some more mumbling. Was there more mumbling somewhere? You have no idea. Anybody else picking up what I'm laying down? Negative? Remember the length of a linked list? You could compute it by traversing it until you get to the tail, in which case you've got to do a linear amount of work. Or you could just store the length, and then you've always got it right there. You increment it when you add one and decrement it when you remove one. So that's why, depending on which algorithm you choose, you could store it, in which case it costs storage, or you could compute it. It doesn't cost storage, but then you have to do more work every time. So you can trade those off. So there is this fundamental trade-off between time, and memory. Does that make sense? All right, like here's an example that actually is a real deal thing. If I were to ask you to compute the product of two 3-digit numbers, that would take you a little bit of time, wouldn't it? Like, even though, like, y'all could do this, it wouldn't be fun, but 987 times 346, yeah? You remember this? You got to do this times this, and then bring it down, and this times this, and this times this, and then you add a 0, and then you do all that, and then you add them up at the end. It would take us a number of steps. You guys remember this algorithm? It was really big in like 5th grade, somewhere in there. Very popular, very popular. Oh, it is an algorithm. It's a series of steps to solve a problem. More on that later. Do you know what one could do if one had a lot of paper? One could compute the product of every 3-digit number. This would be a pretty big table, but you could go through, maybe let's say with a calculator, and compute all the products of 3-digit numbers. You with me? It's a big table. And technically, because multiplication is commutative, you don't even need the whole table. You just need half of it, right? You don't even need this part. Because 1 times 1 is 1 times 1. Okay. If we had this table, how much work would it take to compute 987 times 346? You look at the table. You go to 987, there's 987, and then you go down to 346. And if you could very quickly just know how far to go, in essentially 2 steps, you could get the solution, having done no actual multiplication, if you just were given this table. You with me? So this is an example. I think it's a really simple example of how you could trade storage and time complexity back and forth. If you have the table, you don't have to do any math. You just look it up, and it's pretty easy. But you've got to pay the price in storage. Do you want to hear an interesting technical anecdote? Thanks, Josh. Appreciate it. This underlies one of the worst business issues, like business ethics issues / technical issues that's ever happened, I think, in the history of computing. And I was there for it. I was alive 3,000 years ago when this happened. Intel, on their Pentium processors, when they did division of 2 numbers, instead of actually doing the division algorithm, which is hard and slow, they just created a giant table in memory of division so that it was really fast to do division for a certain range of numbers. You with me? So it's the same idea, but instead of a multiplication, it's division. But it's still just a lookup because they were spinning their transistors, basically, the transistors that they put on the chip. They made them into memory instead of into compute because it was a better use of transistors. Okay. So there's this mathematician who's doing math on a Pentium processor, as one does with a computer, and he discovers that the processor is returning incorrect results. Now, how he did that, I don't know, but he realized when you do this division, it's wrong in the 4th or 5th decimal place. But he digs into it and discovers it's not just him. This processor that cost, like this is back in the 90s, so computers are way more expensive. I mean, so he's paid $1,000, $2,000 for this computer centered on this processor, and it computes some division slightly wrong. You with me so far? So he tells Intel, hey, there's a problem in your processor. Turns out they put some bad data in the table. So that's how it does division, is it does the table lookup. It's not something that's wrong with any algorithm. The wrong data is on the chip. The table itself is wrong. There's no way to fix the chip. The only way to fix it would be to get a new chip, to swap them out. Intel says, it's not that big of a deal. You theoretical mathematician, it's annoying. We hear you. That is such a small issue. We're not going to fix it because it would be too expensive. We'd have to like literally replace all the chips of all these CPUs that we've sold. I mean, it was small in terms of the math, but psychologically. So the word gets out, this guy like tells more people, this CPU is producing incorrect results. This spreads through the world, and people like are, I think, justifiably outraged. This thing that I spent $1,000 on is wrong. It produces wrong answers. It doesn't matter that they're slightly wrong in the 10th decimal place. It's wrong. And people won't stand for it. There's a huge like outcry, huge like PR issue. And Intel eventually has to cave, and they create a system where they will mail you a new CPU and you mail in your broken one. And they'll swap it out for you. It costs them millions and millions of dollars, like giant loss, to give everybody a new correct CPU. And that's what they eventually had to do because the PR was so bad. But it's based on kind of this principle of time and memory complexity trade-off. I think now that's a case study in like a business law or business ethics class of like how not to do business. When you sell a flawed product, don't try to sweep it under the rug and say, no, you don't need the correct one. You're fine. You're just a regular person. You don't need a correct CPU. That's basically what Intel said. And can you imagine how that would feel? I think also happy ending, they offered the dude a job, the mathematician that discovered it. Okay. Yeah, I don't know. I don't know if he accepted it. I do know that they offered him one. Okay. I may have gotten some of those details wrong. I think I'm 99% right on the story, but you're welcome to look it up. Intel. Oh, the cool part to me is I had that chip. And the first computer that my dad bought in 1993 was that flawed Pentium chip. So we did the thing where they sent us a new one, and then we had to mail back so like I saw it with. Thanks, man. Sort of calling me old, but in a very like gentle way. So thank you, man. Yeah, that was a reference to this movie called The Lord of the Rings. If Dylan were here, he would have gotten it. Josh, could you please leave? No? All right. I want to throw this in here too. This is not Big O related, but development time also matters. Sometimes implementing a better time complexity algorithm is so complicated and error prone that you might decide we're just going to have to go with the simple option because we don't have the time. Like there's business factors at play here. We got to get something out. We got to ship it. And maybe we make it faster later. Also, if n is not big, if n is relatively small, then we can have a slower algorithm and it's okay. All right, more on that. All this, the big sub-question we have is, how does the algorithm behave when the input size gets bigger? How does it scale? I kind of already mentioned this, but definitely an algorithm with higher time complexity is going to have slower performance in like wall clock. One might ask, sorry, let me say this. It doesn't work the other way. Just because something runs fast doesn't mean the time complexity is better. I think this is when I threw your computer under the bus. That just because something runs faster on my computer than it does on Josh's computer doesn't mean my algorithm is better than his, because we have different computers. And it may just be that the performance difference is not due to the algorithm difference. I mean, very much the same algorithm would run differently on our two computers. So do you see, like, so the complexity is what we're doing in big O. Complexity is the big O. How many steps does it take in a general sense? Performance is how many seconds did it take to finish that? One might ask, why does all this complexity thing even matter? Just buy a bigger computer and you can solve it. Just buy a server, buy a data center. You can solve the problem. And one thing I like to point out from the just use a bigger computer response is that doesn't actually solve all problems. There are some problems that when you do the analysis are so big, buying a bigger server doesn't help you. The traveling salesman is a classic problem that fits in this space. The idea is that you've got a salesman that has to go to N cities, needs to visit each city once. Each of the cities are geographically distributed such that there's a distance between all the cities. You can go from every city to any other city. If you have 6 cities, then you make a choice as your first city. The first city is arbitrary, right? You've got to go to all the cities. So you start at a city, then you've got 5 choices. Choose one of those 5. Then you've got 4 choices. Choose one of the 4, the 3, the 2, the 1. You with me? Those are the number of choices that you have. So this is based on factorial. You can actually then, the total number of distinct routes is n minus 1 factorial divided by 2, because there would be a, it doesn't matter which, you can go forwards or backwards through that order, it's the same order. Does that make sense? Okay. If you have to compute all the routes, all the possible routes, in order to figure out which one's the smallest, this is how many routes you have to compute. So it's 60 if there are 5 cities, 360 if there are 6, 2250 if there are 7. But you see, with just 50 cities, which is really a relatively small thing, this would be like, how do you visit all 50 states? There's 3.04 times 10 to the 64th different possibilities to do that. That number is so big that it doesn't matter how fast your computer is, like the universe is going to end before you finish this. This is more time than there is in the universe. This is like more atoms than there are in the, some giant number. This is too big. It's not tractable. So if you're going to solve this problem, which people have spent a lot of time trying approaches, you cannot brute force it by just trying all the options. So enter big O notation, which is a notation for measuring, specifying how well an operation, an algorithm will scale. So how does it behave when the amount of things that it operates on increases? So that's why there's always an n or some other variable in a big O notation. We're saying as this variable gets bigger, so I guess bigger is this way, as it gets bigger, as n gets bigger in a linear way, how does the operation operate? How does it behave? Said more formally, big O notation is a relative representation of the complexity of an algorithm. So it's relative because we're really just comparing this thing versus some other version. We're not using seconds, right? This isn't absolute seconds. We're just saying if n increases, you're going to do a linear amount of work, or a quadratic amount of things, or a factorial amount of things as n increases. So it's relative. This special word here is called complexity. There's a whole branch of computer science called complexity theory. I guess it's also math that analyzes these kinds of questions. So if I say what's the time complexity of this algorithm, that's synonymous with what's the big O notation for it. So we went through this last time when we talked about it, but if you figure out the exact number of steps in the worst case, the math is messy. This is messy, the adjective, not the player. We don't like messy math. So Big O makes two simplifying assumptions, two simplifying rules. Number one, the constants don't matter in the whole scheme of things. We don't care if something is 3n or 18n. They're both products of n. N is the thing that matters. The constant doesn't really matter. The second thing is the higher order term, the highest order term, is the only one that matters because it's the one that dominates. If we've got an n cubed and an n squared and an n and a 4 billion, the 4 billion doesn't matter. It's a constant and a low order term. The n doesn't matter. The n squared doesn't matter. The n cubed is the thing that will always get biggest. If we can make n as big as possible, n cubed, that factor is going to dominate. Okay, I go through this example, but I really don't want to go through it in detail today. Maybe this should just be today's quiz. Can you add two 3-digit numbers? You remember this algorithm? It's a classic. This one goes back, like it was huge in, what, second, third grade? Second, maybe? If I were to ask you to count how many additions there are in this problem, does that make sense? In the worst case. Brandon says 3. I disagree. But I may need to define my terms.
Because you add the first numbers together. If they are greater or 10 or greater, you have to carry the 1. So then now you have 3 additions.
You follow me, Brandon? So I'm going to say this was 1 addition, and then over here I have this and this. That's going to have a carry as well, right? That's 9 plus 9 is 18, which is 19. Yeah? And now I have this addition and this addition, which is another 19.
Should you count the end?
I could go either way on that one. Do you want to? So you see, Ryan's saying you could imagine here we've got leading zeros, and what's happening here is that we carry a 1 out and do it again. We can go either way, however you want to define that. But notice here, if you have, if you've got 3-digit numbers, the time complexity here, let me not say the worst case number of additions is what? Can we call it? You want to call it 5? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And we won't count the carry out the high order. Does that make sense? We've got 5 additions. If you had 2 4-digit numbers, what's the worst case? You can almost imagine then I've added a 9 and a 9. Ryan says add 2 more. You said add 3 more. Somebody said add. I thought somebody said 8. You think it's 8? Well, 1, 2, 3, 4, 5, 6, 7. If we're not going to count this one, I think it'd be 7. Yeah? If you had 5-digit numbers, can you imagine what that would be? See a pattern here? What's it? And if you had 2 n-digit numbers, you see that? Oh, it's getting low. If you had 2 n-digit numbers, how many would it be? N plus 3? n, you're saying it's 2n minus 1? Does this hold for us? 2 times 3 is 6 minus 1. 8 minus 1, 7. Yeah? So this is the 2n minus 1 is the actual number of additions that we do in the worst case. What is the what's the big O time complexity? 2n minus 1. We get to throw away the constant, and we only care about the leading term, and we don't care about its constant. Yeah? So this is O of n. So this algorithm that we learned in elementary school is a linear algorithm. As you add more digits, you're going to do a linear amount of more work. You feeling that? So remember that. That's how that feels. Linear algorithm feels like this. Let's take it up a notch. You remember this? We mentioned it earlier. It's a little preview. If I were I'm gonna ask the exact same question, which is not how many multiplications are there, how many additions are there in this long multiplication algorithm? And I don't actually want to work it out because it's really gross, but if you can imagine this 1, 5, 6, 6, 2, 5. Do you remember the algorithm? You say this times this is 30, right? And then you put a 3 here and bring the 0 down. At this moment, I'm saying I haven't done any addition. 5 times 5 is 25. And then you add that to get 28. So now I have done 1. So that's an 8, and then I bring the 2 over here. Is this right? 5 times 1 is 5 plus 2, which is a 7. Yeah? So there's additions that you do in this process. If you remember here, I'm going to bring down a 0, and then say 2 times 6 is 12. Now these go away, right? 2 times 5 is 10, plus 1 will be 11, and now I've done another addition. 2 times 1 is 2, plus 1 is 3. We should just finish now. Okay. Now I add 2 zeros. 6 times 6 is 36. 6 times 5 is 30, plus 3. So there's another add there for 33. And then 6 times 1 is 6, plus 3 is 9. And that's it. So just to do this part, if I count additions, which I am, for carries, I've done 6 additions. What do we do here with these 3 numbers? You add them all together. So if I'm still going to count adding 2 numbers together as an addition, that's the way I'm counting, is binary, the binary addition. Not that the numbers are binary, but that it takes 2 things. Then I'm going to have 1, 2. If you think about the worst case, if I can jump up to that, right, you could say there's 1, 2. It's possible that I carry something out each time. So this would be 3, 4, 5, 6, 7, 8, 9, 10, 11 ish. Depending on how you count, I could see this one I might be tempted, Ryan, to actually, one could imagine that there's zeros here to fill up the whole block. You see, if I added those zeros to fill it out. I forgot how many. Did I come up with 11? So there's 11 more here. So there's 16. I did 16 additions to do this. So we can walk through the same process. 17, thank you. Yes, 17. So when, if I did this, when n is 3, then I did 17. Can you imagine what happens if I add a number there? Can we think about, I don't want to do the math. If I add another number here, what happens to the width of this? It gets one bigger, right? What happens to the height of this? It gets one bigger. So the total number of additions, can you see, is always, you can definitely see it if I add these extra zeros. The total number of additions is always the width times the height minus a few. Does that make sense? Does it? Do you see how if I added this extra digit, then I'm going to have a whole other row? If you have to take the width times the height, the width is always, looks like to me the width is about n plus 1, and the height is always n. In addition to that, you've got your carries as well, which I think the carries are like, we came up with 6 carries, right? 6 carries. I think that's a 2n. If I can just skip to the end, we'd have to do some more checking to see. So if this is the actual number of operations, there's probably a minus in here as well that I'm skipping, because you might get to skip this one. What's the big O of n plus 1, n plus 2n?
Well, if you multiply the n's and the n, you get n.
This is algebra. You okay with this algebra? Just multiplying this through. This is a low-ordered term, so I don't care about it. I'm going to throw it away. I can throw away all the low-order terms. There's probably some constants, too, that I skipped, and I knew that they wouldn't matter, so I didn't even keep up with them. And now we don't even have a constant, a coefficient on the n squared, but that n squared really is, O of n squared does describe this algorithm. And I like to go through this example because this is 2 algorithms you've known for a long time, but you didn't know big O time complexity, but you did. Because didn't you feel how much harder this was than addition? Did you feel it in your soul? You felt it, right? And what you felt was, to me, you felt the time complexity. That's why it feels so bad, is because if you add 1 digit, if you're doing addition, you're just going to do 1 or 2 more steps, a linear increase. If you do this in multiplication, it is not 1 or 2 more steps. It's going to be quadratic. It's going to be a squared factor of more steps, and it's so much worse. And that's the big O time complexity. And on the whole, that's why we don't like n squared algorithms. And if the best you can do is n squared, it's really not a great algorithm, right?
This is only including addition.
Yes.
Right? We aren't even including the multiplications.
Right. Right. And that is another big factor in big O. I appreciate you pointing that out. When we analyze big O, we're generally like kind of only measuring one thing. We're counting one thing. And that may be different. So let's look at these algorithms. This is, I think, technically in Java syntax. That's almost exactly like C#. So basically, this should be lowercase s in C#. In Java, it's capital S. So that's it. Look at this algorithm and tell me, n here is the number of strings in this array of strings. Yeah? So the question is, what's the big O time complexity of this algorithm? This is something that I'm going to want you to do on the test, so that's why I wanted to go through this. How much, so just marinate in this for a second before we hear the answer. How much work do we do? You can add up kind of how many lines of code get executed to do what this does. So we're going to have to figure out what it does. What is nice is I actually put a reasonable name here, is first element null. And I say if strings at 0 equals null, return true. Otherwise, return false. So I would say in this statement, you're always going to execute this line, and then you're either going to execute this line or this line. What would be the big O term for this complexity? O of n? O of n, where n is the number of things in the string. Okay? O of n. You feel good about that? Feeling good? We got to wager push-ups on it? You feeling that good? What's that? Did you hear what he said? Say it again, Joshua, louder. So if something's O of n, that means if you've got 1,000,000 things in the array, it's going to be 1,000,000 times slower than if there were just one thing in the array. Is that how this works? Tristan, you had a response. Do you want to chime in here? Tristan says it's O of 1. Why would you say that? Make your case. You convinced, Brandon? No. We didn't wager. We'll save that. We didn't go down on it. Okay. So this is an example of a constant time algorithm, which we would call O of 1. Okay, O of 1. What if you had gotten the 100th item out of the array? Would that change things? Nope. Because I mean, that would still fail in a constant time. Does this make sense? So if you have no loops, then I would lean very strongly into thinking that this is constant. I suppose if this weren't an array, if this were a linked list of strings, and you could index it and get so in this case, it wasn't the 0th one, but the nth one. And we knew it was a linked list. In that case, it would have to be different where you're getting the nth thing. But even if you were getting the, no, it would have to be the nth thing. If you're getting the nth thing out of a linked list, you're going to have to traverse it, and that's going to take n amount of work. Even if you couldn't see the traversal in here, if it's calling code that does more work, then you've got to consider that. Now, that's a little deeper than I meant to get for now, but does that make sense? What we're knowing by this is that to access a random value in an array, an arbitrary value, is a constant amount of work. Okay, now I've got contains value. I have an array of strings and a value. I'm iterating through the indices from 0 to strings.length minus 1, saying, does strings at I equal the value that was given? And if so, it returns true. If we go through the whole for loop and never find string at I equal value, then we return false. Yeah? What would you call this time complexity? You want to think about this for a second? What are you feeling? That's what I'm asking you, bro. You think it's n? Other thoughts besides n? O of n. This guy. Oh. Okay. I thought you were correcting him. But I will say, but if I ask you to write this on the test, you must write the O. Like, that is essential to write the O. I know you would have done it. When we're saying it out loud, I would always offer forgiveness, but yeah. So everybody agrees this is O of n? We put push-ups on it? 10 push-ups. You're not betting any push-ups on time complexity? So in the worst case, I would say the worst case is this value isn't in the list. How much work do we do? If you were to break it down, you'd say you set I equal to 1, maybe that's 1 unit of work, sorry, I equal to 0 is 1 unit of work. You've got to check I is less than strings.length like n times, and then you've got increment I n times. You do this check n times, you never get n, so that's 1 plus n plus n plus n. That's like a 1 plus 3n. And then when you never find it, you return false, which would be like another 1 if we're counting like lines of code. So what was that? That's 2 plus 3n. But in big O terms, we don't care about the little guys. That's just n. And on the whole, you don't even have to like walk through all that detail. You know what I mean? Like that. How many times do you go through the loop? That's the thing that's going to almost certainly determine the time complexity. Okay. That's not the way this works. I didn't wager push-ups. I don't do push-ups for being right. Y'all do push-ups for being wrong if you agree to the terms of the deal. Okay, so this contains duplicates. I've got an array of strings, and you'll see that there are 2 for loops. Looks like they go from I equals 0 up to the length j equals 0 up to the length. If I equals j, we continue. Have we seen the continue statement before? What does continue do? It's a little bit like break. Break jumps out of the loop. Continue just means like skip to the next iteration. Just don't do any more work. Yeah. So as long as I is not equal to j, we compare strings at I to strings at j. If they happen to be the exact same, we return true. If we get through both for loops, we return false. So this is the naive, easy way of checking for duplicates in a collection, is to essentially compare everything to everything else. Except don't compare yourself to yourself. That's why I and j, we skip this, right? Because the thing at 1 definitely equals the thing at 1. There's no point in comparing it to itself. We should skip those. But if the thing at 1 equals the thing at 13, then that's a duplicate. So how much work does this algorithm take in big O terms? You said O of n squared? 2O of n squared. What was that? O of n squared. Ronaldo? Thoughts? Is this O of n? Is this constant? You think it's O of n? So the amount of work that we do is linear. If you have 10 times as many things in the array, you're going to do 10 times as much work. Garrett, thoughts on this? No thoughts whatsoever. Okay? What's that? His head? Oh. Ethan, how about you, man? Does this look like anything to you? You going with O of n squared? Josh was saying O of n. This is the same thing as this? Okay. Cecily, thoughts? You don't want to commit to anything? It's good? It's good. All right. Bo? Okay. Andrew? Solid agreement? Yeah? Okay. Very non-committal. Okay. You guys are the kings of non-committal. I would hate to go out to dinner with y'all. Where do you want to go out to eat? Tristan, thoughts? Going with n squared. Did you already? Have you voted? Okay, you're Jordan. I know I missed somebody. Okay, it's your grade. You can definitely do that. In cubed. Okay. So this is a classic n squared algorithm. We've got this inner loop that happens n times. And the outer loop also happens n times. But how much work happens for every one of those outer loops? N. So you do in work the first of the outer loop, and then another in, another in, another in. So that is n squared. Okay, so this is n squared. Yeah, please.
Pieces where that it does not have an end method time.
So, but that is a good cheat code, and that's going to probably get you right on 80, 90% of the time. And there's just some weird oddities that would not be that. But looking at but that's a good cheat code, and I want y'all to remember that. If you have 3 nested for loops, I mean, a for loop in a for loop in a for loop, and each of them goes up to the length, what do you think that time complexity would be? O of n cubed, yes.
You have a scenario where it
There is a word for all of them, bro. Cubic is n squared, and it's not quadratic. That's 2. It's like quadic or something. Do you know? Quartic sounds right. Hmm.
I'm talking about like n squared cube.
Oh, and not say the word for. I got you. I got you. Okay. Okay. All right. This one is tricky, but I'm showing it to you because, for one, we already talked about binary search, and for 2, this is an important class of algorithms. So you remember binary search? I think we lined up along this wall, and we said, guess the number. We have no idea. Remember, your pieces of paper had numbers, and you essentially say, I'm going to choose the middle number. Am I too big or too small? It's got to have you got to have a sorted list. This is doing this. You see this while loop. You start with the position of -1. As long as the max is greater than the minimum and the position is equal to -1, we go into this and we say, hey, compute the midpoint. If the array at the midpoint is equal to the value, then the position of the thing we're looking for is the midpoint. So the whole point of this is to set position equal to the index of the thing we're looking for. If the array at the midpoint is less than the value, then we set the minimum equal to 1 more than the midpoints, where the midpoint is the index. And if the array at the midpoint is greater than the value, then we set the max equal to the midpoint minus 1. So basically we're saying, look in this half, or look in this half. So every time we go through this while loop, we're actually cutting the search space in half. What's the name of that function that does this? You remember that? Log in? Who said that? He's a logarithmic master back there. Yeah. Sometimes people put parentheses around this. Sometimes they don't. I could go either way. So when you have this scenario where you're cutting the search space in half, that's much better than, it's not like you're decreasing it by 10 each time. That would still be that would still be like a linear number of times. But when you're decreasing the size of the problem by a factor, in this case it's a factor of 2, that's logarithmic. If you had a problem where you decreased the size of the problem by 3, like divided by 3 each time, that would still be logarithmic. And it's really just a constant difference. So really, at this point, we would say this is log base 2 of n. You remember there's a formula for converting between bases of logs? Can anybody, like, you can go from the log base 2 of something to log base 10 of something, right? And I think it's just like, it's some constant. it's log base 10 of 2 or the log base 2 of 10 or something. It's been a while. But this is just a number. We don't care about numbers. So that's why you don't even normally write the base on here, because it doesn't matter. So this is a classic. Binary search is a logarithmic algorithm. Yo.
Is the presence of a while loop?
No. But it does mean if you got a while loop, you're going to have to be more careful in your analysis. You can implement any for loop as a while loop. You with me? Like you just, right? You put your I equals 1 before the while loop. You put your I plus plus somewhere in the while loop. And then the I is less than strings.length is the condition of your while loop, or the opposite of your condition. Yeah? Okay. So as we sum up here, and then we're going to switch gears and talk about practice exercise 3. I'd like for you to just like feel how these numbers grow. I know it's hard to get a conception of numbers. I've got graphs coming up too. But O of 1 constant is 1 for 10 things. And it's 1 for 100 things. That's easy to conceptualize. So it's the same amount of work. O of n is 10 for 10 things and 100 for 100 things. Log n is 3 for 10 things. It's 7 for 100 things. So this is why we like log. I mentioned the Amazon database, right? Like, even if you got 1 million things, if you do binary search on 1 million things, that's just 20 steps. 20 is nothing. N squared, though, right, is much worse. N squared is like 100 for 10 things and 10,000 for 100 things. Let me fill in this table with the other common time complexity classes. So n log n is a really popular, common time complexity, in my opinion, for clever algorithms that would be n squared without the cleverness. So what we'll see next semester is that the best sorting algorithms that are regular sorting algorithms are n log n. The dumb sorting algorithms are n squared. And you can see here by swapping out one of those n's for a log n, how much better you do. 30 and 700, yeah. Some algorithms are exponential, so we would call this exponential. Whether it's 2 to the n or 10 to the n, it doesn't matter what the base is. If the n is in the exponent, it's terrible. You see how quickly this explodes here. But really, for this, our worst case, the guy that we hate the worst, no offense to those of us who love factorial or exclamation points, is the factorial. So if you're in a factorial sense, which is, you know, factorials are in many combination permutation. Remember that combination permutation formula? If you're in a scenario where you've got to compute all the combinations, you're likely in a factorial world, and that's the worst. So I found this on the internet, and I did clean it up to make it a little bit more FHU appropriate, but I thought this was a nice, fun way of kind of internalizing what big O means. So O of 1 constant is like, oh yeah, this is amazing, constant. O of log n is like, oh, nice. That is going to scale very nicely. O of n is, okay, it's linear. It's going to get big when stuff gets big, but just at the same rate. N log n is like, okay-ish. We're probably doing something complicated. This is about the best we could hope for. O of n squared is an oh my. I'm immediately feeling that's going to get pretty big if n is at all big, and I'm probably going to feel that slow down. O of 2 to the n is an oh no. This is really, you can only deal with very small n's if you're exponential. And then lastly, O of n factorial is oh crap. You got to have very small n's before this just breaks down, or it's just so slow that you could never do it. So this is kind of FHU appropriate alternative big O notation feelings, okay? This is almost like these things are so different that just graphing them, I don't know if you can tell, like O of 1 completely disappears because it's just a straight line. I just put it with no constant. The O of log n looks like it's a straight line because it's that small in comparison to just, you see O of n is in green here. So that's, yeah. This is O of n log n, how it would grow. Just n squared, so this is the parabola, is going to grow like this. Exponential looks like it's going straight up until you look at factorial, which is like, oh no, that's actually going straight up. It's not actually straight up, but I mean, almost effectively is. Okay, so that is big O, and I'm intentionally doing this lecture again-ish because I'm going to ask you questions like this on the test, especially giving you code that I'm not going to label. It's not going to be called is first element null. It's going to be called mystery 3 or something terribly named so that you actually have to look at what's going on in the code to figure out the time complexity. So you're going to get the code and then have to write the time complexity for an algorithm. Okay. And I think probably being able to write out these, what is this, 7 time complexity classes is something else that I want you to be able to do. Because in some sense, for most problems, any time complexity question is essentially multiple choice. So let's use that in our favor. You know what I'm saying? Like, technically there's an infinite number of time complexities, but I've never seen a problem where n to the 6th was the answer. You know what I mean? Like, that's not what we normally ask about. So I want you to just, like, do well, even if it's still a little hard. Okay. Practice exercise 3. I don't know if you saw my video. I made a terrible, horrible, no good, terrible, badly mistake, which was in my stack, in push, I used prepend, which isn't really defined on a linked list apparently. I didn't dig into why that was the wrong word, the wrong method. Add first is what we wanted. Did y'all get this message? So change this line, line 39 in my code, in push. Do not say prepend. Do not. It does nothing, and then everything fails because nothing ever gets added to the linked list, which means nothing ever gets pushed on the stack. So make sure that this is add first. Did you find that? So when you push, the way we did it, we added to the beginning of the linked list. The top of the stack was at the beginning of the linked list. Questions? Tristan, does that side glance mean something? Okay. Another thing that I added that you're going to have to add, I'm sorry, I guess I ran out of time last time. I have defined a toString for a stack and a queue. The stack is pretty reasonable. The queue is really arbitrary, but you have to define, you have to use exactly my toString to pass the unit test, because I'm going to print your queue out and then make sure that the string matches. So I believe that this is the correct implementation of toString. I did put this in the code that I sent out so that you can just copy paste it. Did you see on the GitHub? You can just copy paste this. Didn't I put it on Discord? I think did I put it on Discord and Canvas? So notice I've got this result string, and I traverse the linked list. And starting from the top of the stack, which is the first, I actually create top of stack, next to top, the one under that, the one under that, the one under that, all the way down to the bottom. Does that? So it would print out a stack just as a list of numbers separated by new lines. You know, the /n is how you create a new line character. So this is how a stack will print out. And I'm using this to test your stack. So you need this code, where the top of the stack is, hold on to yourselves, on the top of the stack. Yes. Okay. You with me here? All right. Q is the tricky one. I created a blank Q class that implements IQ in T. I guess you'll have to do this. I didn't do this ahead of time. And its toString follows this format, which this is really arbitrary. I could see it in many ways. But this toString starts off with this angle bracket. It's almost like a tag back. And then it has from the back to the front, from the left to the right, it'll go back, and then the back of the Q, the second to the back of the Q, boo, 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 all the way to the second to the front, and then it ends with the word front. And there's a little arrow character between them. So when I print it out, I had the Q go from left to right, which is arbitrary because it could go from right to left. Does that make sense? So this one, just copy paste this and make this the way that your data structure becomes, well, I guess you may have to change this. I am assuming that the end of the linked list is the end of the queue. And the beginning of the linked list is the beginning of the queue. You could map that in the other way, but it seems a little confusing to me. Yeah. If you go to github.com/FAQ/CIS273-FA25-practice exercise 3.
So just go.
Did I put it on Canvas?
Yeah, practice exercise.
Seems like something I would have done because this was pretty essential. So this is my original code. And if you go under practice exercise 3, and then the Q, it's not implemented, but it does have this toString here. Yeah? Is that the home page?
If you go to your copy of the it on GitHub, then you can remove your name.
So wait, did you get it, Joshua? So practice exercise 3. Right, go under q.cs or stack CS. There's one in both. There's also one in deck. A deck is a queue, so I just completely just copied the string on that. Is what? Usually URLs are not case sensitive, but occasionally they are. So you can, technically it should be capitalized, I suppose, because that's what I named it. But I would suspect that, oh no, it is capitalized. Interesting. It is case sensitive on GitHub.
I mean like the top version, where it's like just the practice exercise 3 tree, not the main.
Huh?
Show you. You see here, I have the URL in all lowercase.
Yeah. So that works.
So is this because this is not
Yeah.
one of these end classes.
Yeah.
Once I go into the tree,
Yeah.
then
Yeah. So did y'all get that working? Yeah. So you want to copy paste this toString into your stack, the toString that's in my queue into your queue, and the toString that's in deck into deck, which is the exact same thing as what's in queue. I did go ahead, and I think you should go ahead, create the empty files for queue and deck, and then say that you implement the IQ or the iStack or the iDeck interface, and then at least you'll have placeholder, like in this, not implemented, so then it can actually build. You will also want to get my unit test. Again, apologies, I was not on the ball on that, but coming into unit test and the unit test CS, and copy paste all of my unit tests on top of your unit tests, then these have the corrections to the exception syntax. Yes?
So, you have in the ICE facts, you removed all the curly braces, all that, right?
I changed the namespace stuff. Is that what you mean?
Yeah. I think I figured out what it is. Yeah. Thank
Okay.
You. It
Here.
was a semicolon, but it was telling me.
Yes, Garrett? I didn't give you the Q file in class last time, so if you want to, you can just copy paste what's in this queue into yours as a starting point. This throw new not implemented exception is what you get when you have Visual Studio Code implement the interface for you, which is just kind of create these empty slugs. And then it does, in fact, implement the interface. It just doesn't fully do it. Other questions? Yo. So deck is generic in T. Oh, right, yeah. I made it after the fact. You should make one too. Oh, come in here to practice exercise 3. Right click, new file. Deck 2.cs. Yeah. I do have these two empty queue exception and empty stack exception objects defined for, like, see, they're subclasses of exception that I am asking you to throw if you do an operation on a empty stack or an empty queue. That would be like popping or dequeuing. Other issues on this? So you want to copy over my new unit test, create at least the placeholder files for deck and queue that I didn't make last time. IDEC defines the shape of a deck. IQ defines the shape of the queue. IStack defines the shape of the stack. I did some cleanup of the namespace to bring it to this newer format that I like better. So now I put namespace and then practice exercise 3 semicolon at the end, and then removed the curlies from around the whole class. Just to remove a level of indentation that looks gross to me. Oh, at the end of practice exercise 3? Gotcha. That'll get you. Yes. As you can technically do that, yeah. That would be one way of solving the problem. Okay. Questions or concerns on this? When is this due? Saturday. Okay. So next week, I'll be sharing lab 1, I guess, where we're going to use stacks and queues to solve some interesting problems. So this will be more challenging than a practice exercise, more fun than a practice exercise, I should say, because we're going to see not just how do we make this data structure that we should never make, like we should always probably just use the one that's built in, but how do we use it to solve real problems? So I've got some interesting stuff to do, kind of a special kind of calculator and some other algorithms that are well suited to stacks and queues. So I want to make sure y'all can do this well. I think this should be a relatively easy assignment because the linked list, we're using Microsoft's linked list. Don't use your linked list. Use Microsoft's linked list. It has the methods that we want. Add front, add back, remove front, remove back, and mapping that into stacks and queues is relatively straightforward. To think, am I just going to always add and remove from the front? Am I going to always add to the back and remove from the front? We make sure I don't do something to an empty linked list, which would be an empty queue or stack. So I'd like to see a lot of hundreds on this. Let me know if you found issues with the unit test after you pull in mine. So we're prepping so that we can have an awesome test on Tuesday next, the 11th, which is over stacks and queues and decks, linked lists, singly and doubly linked, and array lists. That's sort of a comparison. Remember, array lists kind of set us up to understand why a linked list is better. And big O notation. Big O, which we have re-hit today. So looking forward to seeing you next week. I hope it's a good weekend. See y'all.